the name of Almighty God, I'm Master Sankoshi, and today I want to talk about multibody dynamics module in quantum multiphysics simulation software. Today I want to talk about clearance joint formulation in three dimensions. The formulation of the clearance joint is similar to a ball joint except for the translation constraints. Analogies in two dimensions, the clearance joint formulation is similar to a hinge joint. Instead of translation constraints, a penalty-based formulation is used to enforce that the distance between specified points on both selected components is between the clearance distance. The penalty force is computed as Fj is equal to, if gap is less or equal to 0, we can have a minus Pj multiplied by gap and 0, where Fj is a joint force magnitude and Pj is a penalty force input having a default value of 0.1 multiplied by diagonal E equal. In this expression, A equal is an effective Young modulus, and the diagonal is the geometric diagonal to the bounding box of the geometry. The gap variable is the difference between the clearance C and the distance between and the connection points D. Gap is equal to C minus D. The distance between connection points D is calculated as D is equal to absolute X source plus U source minus X destination plus U destination. Here, X source and X destination are the four locations of the two connection points, and U source and U destination are the corresponding displacements. Fixed joint theory. The fixed joint rigidly connects the two components and doesn't allow any relative motion between them. It doesn't add any degrees of freedom. The following is an addition to the prismatic joint theory, some of which is also applicable for the fixed joint. Now I want to go through the fixed joint formulation. Constraints are added stating that the both parts have the same value of displacement and rotations at the center of joint. In three dimensions, six constraints are added. C destination is equal to USC source and BA destination is equal to BA source. In two dimensions, three constraints are added as USC destination is equal to USC source and phi destination is equal to phi source. The position of the center of joint only affect interpretation of the joint forces and moments. Now I want to go through the joint elasticity in fixed joint. The elastic degrees of freedom are written as U1 is equal to U1 E1 plus U2 E2 plus U3 E3. Theta A1 is equal to theta 1 E1 plus theta 2 E2 plus theta 3 E3. Now I want to go through the distance joint theory. The distance joint maintains a specified distance between two points that are connected to a pair of attachment or rigid domains. As a default, the initial distance is maintained so that the joint can be considered as a rigid link with ball joints at both ends. It is also possible to vary the distance so that the joint acts as a telescopic link. The following is an addition to the prismatic joint theory, some of which is also applicable for the distance joint. Distance joint formulation. The formulation of the distance joint differs completely from the formulation of the other joint types. Only a constraint is applied to maintain the distance between the specified points on both selected components. This distance constraint can be written as x absolute XCR or source plus U source minus parentheses X destination plus U destination is equal to absolute X source minus X destination plus delta. Here X source and X destination are the unformed locations of the two connections point, and U source and U destination are the corresponding displacement. It is possible to vary the distance between the two points through the extension value delta. The constraint can be simplified and is used in the following form: U source minus U destination multiplied by U source minus U destination plus 2 multiply U source minus U destination multiply X source minus X destination is equal to delta to the power of 2 plus 2 delta, absolute x source minus x destination. Now I want to go through the universal joint theory. And universal joint, also known as Hooke's joint or Cardan joint, is commonly used to transmit rotational motion between shafts that have different orientations. Physically, this joint is made of a pair of hinge joints oriented perpendicular to each other, connected by a cross shaft or gimbal. This joint is kind of abstract joint where the gimbal is not modal and both the shafts are directly connected to each other. In general, this joint is used to transfer mechanical power from one shaft to another shaft. The added degrees of freedom in this joint are the relative rotations about the two legs of the gimbal that from the joint axis and second axis. The following is an addition to the prismatic joint theory, some of which is also applicable for the universal joint. Now I want to go through the joint axis and local coordinate system. In this joint, the initial orientation of input and output shafts are based on user inputs. The initial axillary axis is defined as perpendicular to the plane span by the shaft. For example, E axillary 0 is equal to EI 0 multiplied by EO 0. In both the shafts have the same initial orientation. The initial output shaft's orientation in this expression is replaced with an arbitrary axis, which is not parallel to the initial input shaft orientation. You can also define the auxiliary axis explicitly. In this case, the projection is made in the plane perpendicular to the initial input shaft orientation to ensure the orthogonality of initial auxiliary axis and initial input shaft orientation. The initial axis of connection, the gimbal and input shaft or initial joint axis can be defined as being the same as the auxiliary axis. E10 is equal to E auxiliary 0. Alternatively, the initial joint axis can be defined by rotating the initial auxiliary axis E auxiliary 0 about the initial input shaft orientation EI 0, which is specified theta G 0. E10 is equal to E auxiliary 0 cosinus theta G 0 plus E I 0 multiplied by E auxiliary 0 sinus theta G 0 plus E I 0 multiplied by E I 0 plus multiplied by E auxiliary 0 multiplied by 1 minus cosinus theta G 0. The initial second axis and initial third axis are formed by E20 is equal to E10 multiplied by E0 10. E30 is equal to E10 multiplied by E20. The rotated local coordinate system computed as E1 is equal to RS source, E10, E13 is equal to R destination, E20, E3 is equal to E1 multiplied by E2. The current orientation of input and output shafts is computed by multiplying the initial directions with the corresponding rotation matrices. EI is equal to R source EI 0, E 0 is EO is equal to R destination EO 0. Now I want to go through the universal joint formulation. The formulation is similar to that of a hinge joint, except the definition of the relative quaternion, which is written as IR and BR is equal to R2 BR2 multiplied by IR1 BR1, where IR1 is equal to cosinus theta 1 divided by 2, IR2 is equal to cosinus theta 2 divided by 2, BR1 is equal to sinus theta 1 divided by 2 multiplied by 1, BR2 is equal to sinus theta 2 divided by 2 multiplied by E2. Joint elasticity in universal joint, the elastic degrees of freedom are written as U1 is equal to U1 E1 plus U2 E2 plus U3 E3 theta E1 is equal to theta 3 E3 post-processing variables. For the universal joint, some extra variables for use in post-processing are defined angular velocity and total rotation of input and output shafts. The angular velocities and total rotation for both input and output shafts are computed as omega I is equal to omega I multiplied by EI omega 0 is equal to omega 0 a 0. Theta I is equal to integral omega I derivative of time. Theta O is equal to integral omega O derivative of time. In order to evaluate the integrals, two extraordinary degrees of freedom are created for each universal joint. Now I want to go through the torsional moment in the shafts. The torsional moments in the input and output shafts are computed using MI is equal to MIE multiplied by EI. MO is equal to MO multiplied by EO. Angle between shafts. The angle between the shafts, bend angle, beta is computed using beta is equal to arc cosinus EI multiplied by EO. Now I want to go through the theory for joint constraints. Constraints are used to restrict relative motion between the two components sharing a joint. You can specify the upper and lower bound of relative motion. Applying constraints on the relative motion can be interpreted as placing an imaginary stopper that restricts the motion of destination attachment with respect to the source attachment. Prescribe direction, translation constraints, rotational constraints, inclination angle constraints, and axial rotation constraints are discussed in this section. Now I want to go through the translation constraints. Translation constraints are available for the prismatic joint, cylindrical joint, screw joint, planar joint, slot joint, and radius slot joint features. The maximum relative displacement U maximum and minimum relative displacement U minimum can be prescribed. The activation condition for the constraint is U is greater than U max, and u is equal to is less than u minimum. For planar joint with the radial constraints, the activation condition for the constraint is ur is greater than u maximum. If the constraint radius prescribes the maximum relative displacement in radial direction, u maximum, the relative displacement in radial direction ur is computed as the distance between the constraint center and the initial position of the center of the joint. A penalty method is used to enforce the constraints. And now I want to go through the penalty method. The constraints on the relative displacement is enforced using a stiff spring between the components. The stiffness of the spring is defined by the penalty factor. When the constraints is activated in the dynamic analysis, the time steps are reduced in order to conserve the momentum in the system. The default value of the penalty factor Pu is evaluated as Pu is equal to the derivative of a u based on the time divided by delta u max to the power of 2 MAE. The numerator in equation 3-1 is an assumed relative velocity between the components when the constraint is applied, and the denominator is a maximum allowable penetration. This ratio of the relative velocity and the maximum allowable penetration decides the required stiffness of the spring. The penalty factor. The default value of this ratio is 10 to the power of 3, 1 per second. This could, for example, be a penetration of 1 millimeter with an impact speed of 1 meter per second. You can change this ratio based on the dynamics of the system and the allowable constraints violation. For a very high penalty factors, the solution can be inaccurate unless the tolerances are tightened. The factor ME in the penalty factor expression is the effective mass at the joint, defined as ME is equal to M source, M destination divided by M source plus M destination. The source and destination masses M source and M destination are defined as the mass of the domains attached to the source or destination attachments. In case of flexible components, the mass of the attached rigid domain. In case of rigid components, the following assumptions are made in the definition of the effective mass. Both parts are free to move if only one of the parts is free. You should use the mass associated with that part as the effective mass. The computation of M source and M destinations considers the domain that are directly adjacent to the source and destination attachment. These domains cannot be the only parts affecting the dynamics of an impact. The computation of image source and image destination also don't account for the mass added using added mass features or mass and moment of inertia features. The default value for the maximum time step allowed in order to capture the event accurately is calculated, such as delta time maximum is equal to t divided by 2 divided by 30, and t is equal to 2p square root MAE divided by PAU, where t is the time period for free vibration of a spring mass system having a stiffness equal to the penalty factor and mass equal to the effective mass, as can be seen from the expectation expressions above. The default maximum time step is approximately zero point 0.1 millisecond. The constraint is violated for half of the period t divided by 2 to capture the phenomena accurately, approximately 32 times. Steps are used. There is a trade-off between accuracy and computation time. A larger number of steps reduces the maximum allowable time step and increases the accuracy in conserving the momentum. However, it also increases the computation time to prevent the solver from taking time steps larger than maximum allowable time step. The penalty factor actually uses a PA mu is equal to PU plus U greater than U maximum, and U is less than U minimum multiplied by if delta T is greater than delta T maximum infinitely and also 0. This means that the modified penalty factor PA mu is equal to given penalty factor as long as the time step taken by the solver is smaller than the maximum allowable time step. If the constraint is violated and the time step taken by the solver is larger than the maximum allowable time step, the solver is forced to decrease the time step. The penalty factor is not modified for quasi-static and stationary parametric types of analysis because the conservation of momentum is not relevant in these cases. The force required to constrain the relative motion is FAU is equal to minus PU mu multiplied by U minus mu max, U greater than U maximum, minus PMU is multiplied by U minus U minimum, U is less than U minimum. And the third element is zero for otherwise. To enforce a constraint condition, a virtual work contribution is added when constraints are active. Delta W is equal to FAU multiplied by delta U. In the case of planar joint, relative displacement of the considerate along the user-defined axis, the constraints direction oriented in a plane perpendicular to the joint axis. The relative displacement in the constraint direction UC is equal to U2 U2 plus U3 U3 multiplied by RL source ESC, where ESC is the normalized constraint axis given by the user. Now I want to go to the rotational constraints. Rotational constraints are available for the hinge joint, cylindrical joint, screw joint, planar joint, and reduced slot joint features. The theory for rotational constraints is similar to what is described above for translation constraints. Here, the penalty factor should be considered as a torsional spring. The effective mass is the default penalty factor is replaced by an effective moment of inertia having an analogous definition. Inclination angle constraints. Inclination angle constraints are available for the ball joint and slide joint features. Here, the relative rotation to which the constraint is applied is the inclination of the destination axis with respect to the reference axis, also called an inclination angle or polar angle. The reference axis can be chosen as the initial source axis, initial destination axis, or as a user-defined arbitrary axis. The reference axis is always following the source attachment. The constraint is applied only on the upper limit of the inclination angle. The upper limit of the inclination angle should be less than 180 degree. The constraint on the inclination angle is independent of the azimuthal angle and cannot be a function of azimuthal angle. You give the maximum relative inclination angle theta maximum as a limit on inclination of the destination attachment with respect to the reference direction. The actual constraint is applied to the cosine of the inclination angle. So we have cosinus theta is equal to ER multiplied by d1, where ER is the reference axis and d1 is the destination axis. The activation condition for our inclination angle constraint is written as cosinus theta is less than cosinus theta maximum. The default value for the penalty factor and the maximum allowable time step is computed as four rotational constraints. The moment of inertia for the source and destination components are computed about an axis that is passing to the joint center and is perpendicular to both the source and destination axis. In order to prevent the solver from taking time steps larger than the maximum allowable time step, a modified penalty factor is defined as P theta is equal to P theta plus cosinus theta is less than cosinus theta maximum multiplied by if delta t is greater than delta t maximum and infinite and zero. The moment required to enforce the inclination angle constraint is made proportional to the difference in the cosines of the angles rather than to the difference in the angles themselves. This avoids operating with inverse trigonometric functions. M theta is equal to the first element is Pm theta multiplied by cosinus theta minus cosinus theta maximum multiplied by sinus theta maximum. Then cosinus theta is less than cosinus theta maximum. Otherwise, we have a zero. To enforce the constraint condition, a virtual work contribution is added for the cosinus of inclination angle. Theta W is equal to m theta delta theta is equal to minus m theta divided by sinus theta multiplied by delta cosinus theta is almost equal to minus m theta divided by sinus theta maximum multiplied by delta cosinus theta. So thank you so much for watching my tutorial video until the end. Today is the 8th day of June 2026. Time is 6:07 p.m. Also, you can download the proper and appropriate quantum multiphysics simulation file from github.com/masterscript.